Okay, so balance the chemical equation. Well, how in the heck do you know if a chemical equation is going on? Is a gas produced? Okay. If it's a liquid solution, how do you know a gas is produced? You'll see bubbles. You see bubbles, definitely a chemical reaction. You'll see a color change. Now, this color change, the problem with the color change is if you're looking at it, you can only see visible light. And if you're colorblind, you even see less light. Okay, so when I say color change, it could be in the infrared. So if you're a bee, you'd be able to see it, or in the ultraviolet, the UV. But for sure, if you see a color change, for sure a chemical reaction has occurred. Heat. That's cold or hot. You know a chemical reaction is going on. Now let's take a cube of ice, for example, sitting in my hand. Is that a chemical reaction? Okay, well, gas produced? No. Color change? Unless my hand's dirty? No. What about the heat? The problem with that example is it's undergoing a phase change. It's going from solid to liquid, which requires heat. So let me ask you another question then. What's the formula for ice?
H2O.
H2O. What's the formula for water? Liquid water. H2O. So is that changed any? No. So if it gets hot or cold, but it's going through a phase change, it's not chemical reaction. So bonds are broken and reformed. So with my melting ice, we start with H2O. It requires heat to go from solid to liquid. So it seems like there's a change in heat. And what is the liquid formula? H2O. So no bonds were broken or reformed. So no chemical reaction. So all of unit 1, there's no chemical reaction going on. Okay, just so everything we're doing, step number 1, we don't need to do. Now, the reason I'm giving you the 4 steps is because when you get to unit 4, everything we do in unit 4 is going to have a chemical reaction. So you got to do number 1 first. But it's a generic problem-solving strategy. Is what's given, what we're calculating, and we have the setup using conversion factors. Okay, does this make sense? Yeah. Now, when you ask a question, I have this stupid blower going on up here. The nice news, it's 100 degrees out, and it's nice and cool in here, but and I'm old. So speak up. No, I was doing this as to how do you handle number 1 on the problem solving list? balancing chemical equation. Well, then how do you know there's a chemical equation going on? So these things are definite clues. There are a bunch of others that are really subtle, but these are the main ones. So don't worry about this process for now. We're going to revisit this in Unit 4. But the main thing is I'm putting this problem-solving list up here. I want you to make sure that you go through all the steps, even though number 1, for Unit 1, you don't have to worry about, but for sure from then on, you need to worry about step number 1. Okay, good question. All right. So again, these are the 4 steps I want you to always use, always. A given is always put on the left. What you're calculating always goes on the right. And we're going to use conversion factors to go from the left given to the right calculated. And you are going to cancel the units. And that's going to be considered your setup. That's going to be considered 90% of the points for that problem. And I told you before, over the summer in my 1A class, a whole bunch of really highly educated students from Davis and University of North Dakota, they did horrible on this. A lot of them got 1% of the points because 1, they missed it. And 2, the setup was goofy. It was no units. So they got no partial credit. I gave them 1 point partial credit because they put something down, but that was strictly a gift, not anything else. So always do the setup. Also, if I cannot follow the logic of your setup, I can't give you partial credit either. So today in dry lab number 2, you're going to be doing lots of these. Lots of these. So let's work through some more examples here. Okay, how many grams are in 3.04 pounds? Okay, so what's given? Look for the number. There's only one number there. That's 304. That's the given. And then the associated units with that given. So we're talking with and I'm going to use parentheses first. I'm also going to use railroad tracks. I want you to get used to I want you to get used to looking at both of them. By the way, you guys in the back, can you hear me okay? Okay. Always tell me you can't hear me because I have no idea whether you can hear me or not. Okay. All right. All right. And what are we calculating? Grams. You know, I really like our other room better for this is okay. So conversion factors. Well, let's look over here. Do we have a conversion factor that goes directly from pounds to grams? Yes, we do. So how many steps is this problem? 1. Okay. So if you don't have one that goes directly, it's going to be a multi-step problem. So 453.59. What is it? Remember to tell you about that steel trap mine? Okay. All right. So how many sig figs is 304? And 453.59. 5. So answer is going to be 3 sig figs. Remember, it's always the least amount. This is in your dry lab too, but don't use that one. Use the one, the digital version I gave you in Canvas. I gave you because, huh?
Where's the file?
Um, but wait. Okay, I would go to modules first. Everyone, go to modules first. If it isn't there, you can go to files. I try to put everything in modules. Okay, so this is the one, the digital version. This is the one you should print out at home. And also I recommend having this in lab today on your phone, because all the bold-faced ones are by definition or infinite sig figs. And don't forget about the 1 gram equals 1 milliliter as well. So it can be 1380 or 1.38 times 10 cubed. Either one's fine. And I leave it up to you to determine whether you consider either one of those awkward or not. Because remember, the purpose of scientific notation is to make awkward numbers less awkward. So for me, 1380 is fine. If you want to put it in 1.38, depends on how your calculator mode is set up. If your mode is set up for scientific notation or engineering notation, it'll convert it to the automatically to the scientific notation. So either one's fine. Okay, so that's a good example of a one-stepper when you've got a conversion factor that has both the given and the calculated in it. Now the question is what happens if you don't have one? Then it's multi-step. So I'm going to talk about the strategies on that. Okay, So let's just modify this as how many kilograms are in 3.04 pounds. And we already know there's one conversion factor that's got grams in it in pounds, but not kilograms. So this is going to be a multi-step problem. So the first thing you want to do is you want to do the given on the left. We've already decided it's going to be a multi-step problem. So the first thing you need to do is cancel out the given. So that means what was it? 359, 339. What was it? Like that? Okay. So that gets rid of the given. Step number one. Always, no exceptions, cancel out the given. Always. Okay. Now the next step is what's left over? What's left over is grams. We don't want grams, we want kilograms. So go to your conversion factor. Is there a conversion factor that has both grams and kilograms in it? Yes. What would it be? And grams have got to be in the bottom to cancel again. Okay. And then when you think you're done, when you think you're done, I want you to look at the problem. Are all the units canceled except what you're trying to calculate? If not, your setup is wrong. No exceptions. So your units have to cancel. Otherwise, it's not set up right. Okay. And then once that's done, make sure you've got numbers in all the conversion factors. Because conversion factors always have numbers in them. And there you have 90% of the points for that problem right there. So the answer is it okay? So it's 1.38 kilograms, or awkwardly 1.38 times 10 to the 0. And I would much prefer if you put it down as 1.38, unless I specifically asked you to put everything in scientific notation. Okay? Because I think the 1.38 times 10 to the 0 is awkward as heck. Some people don't even know what 10 to the 0 means. Okay. This is an interesting problem. There was a jet that crashed in Canada. Remember I told you the story about my pickup with the kilometers versus miles? Okay, this jet in Canada filled up and they used the wrong measurement system. So they filled up and it was a jet from the United States, so it needed pounds of fuel, not kilograms of fuel. It's on the deal. And they used the wrong one and the plane ran out of gas. Crashed. The true story. And a big time engineering problem happened as well through NASA. They used the wrong units. And one of the rovers got all messed up because he used the wrong units. So this unit bit is real important. I wish the world would just be metric, period. But it's not. It's there are these holdout countries, including ours, that just doesn't. Okay, so what's given here? Okay, so there are two numbers. Remember, I always said look for the numbers. We've got two numbers here. We've got 154 hours, and then we've got 345, another number, but it says pounds. What does per mean? Divide. Ah, that's a conversion factor then, if it's division. So that means that's a conversion factor. Okay, so be careful when you're trying to figure out what's given. The given is just a bare number. That's not a fraction. It's not a multiplicand. It's not an exponent. It's just a number. And there's an associated unit with it. Okay, and do we have a conversion factor that has both hours and pounds in it? No, so it's going to be a multi-step problem. First thing you need to do is cancel the given. First step out of the chute. Okay, well, what do we know about hours? Well, we've got 60 minutes and an hour. Or for all of you steel trap mind, we've got calculations in our head on how many seconds there are in an hour. But if we just go 60 minutes, okay, our units HR cancels. Okay, so we're not down to the seconds yet in our conversion on fuel per second. So now we need to go from minutes to seconds. Now we're down to seconds. And seconds we can use to find out how many pounds we're going to burn in that many seconds. Okay, so what needs to go on the bottom? The what? Seconds, because it's got to cancel. This means we can have .345 pounds per second or second per 345. So which one to use? Okay, first one, yes, because the seconds have got to cancel. Now, the other way to do that would be with you can use either one. So everything cancels except what we're trying to calculate. Again, everything's got to cancel except what you're trying to calculate. Most of the time it's going to be a single item. Sometimes it's a new fraction or a new the answer may be involving a fraction or something like that. But the bottom line is everything's going to cancel except what your units of your calculated value is. Otherwise, it's not right. Now to work this, I was going to say work this problem. We're going to divide by everything on the bottom, but everything on the bottom is a 1. So not a good example. All right, so let's just do this real fast. 1, 4. Okay, so 3 sig figs. How many sig figs is 60 minutes? Is it 61? It's infinite because it's by definition, okay? By definition, that means does not come into the calculation. So that's infinite. Same with this. And then this has got 3 sig figs here. So our answer then is going to be because if you look it up in the dictionary, how many seconds are in a minute or how many minutes in an hour, it'll say 60 exactly. So it's not measured. And in general, if the number doesn't have a decimal in it, there's a good chance that it's by definition. Even if it's got a decimal, and sometimes it's by definition as well. That's why on the conversion charts, I had the boldface ones there for you. Anything boldface has infinite sig figs. Okay, so by definition, that's the key. In other words, it's exact, it's not measured. So same with this. How many times did I do that? Let me do it again. 3. 3.1. Exactly 3, right? So that would be infinite as well. That's kind of a weird one, but it's frequently given in books. And
so let's say that's like 60 kilograms. Would that be 1?
Yeah.
So just when it's time, it's infinite.
Just when it's by definition. Sometimes usually it's a conversion factor. So if we go back to all of these boldface are infinite. So 24 hours in a day, even though it's not 24 hours in a day, if you go by the strict, because the Earth doesn't go exactly at 24, it's off a little bit, but they always say 24. Okay, and if I tell you it's exactly 24, then it's infinite. And it's interesting, an inch, 254. Okay, that's 3 sig figs, right? But it's by definition, it's exactly 2.54 with 100 million zeros after it. So by definition, it's infinite then. I will tell you though, if it's infinite, like this chart, you can use in your tests. In fact, I should just include this as part of your test page. Hey, is that a little better on that infinite stuff?
line, it has. Oh, the value is a lot bigger.
Yeah, it's, okay, it's either by definition or we forced it to be perfect. What I mean by that is, the reason why we don't consider that as part of the significant figures is we forced it to be an integer, not 3.1. You get into that fractional stuff when you get into logarithms in 1B. But as far as scientific notation goes, it's by definition that this has to be an integer. It can't be anything but an integer. So because of that, the sig figs is infinite. So that means that doesn't count for the sig figs, only that. So this number has got 3 sig figs. And when we balance equations in unit 4, we're going to be having coefficients out in front of each part. And we're going to force them to be perfect. So guess how many sig figs those coefficients have? Infinite. Because we're forcing them to be perfect integers.
So it's like we're doing a equation like the one we're doing right now, and it's a goal that's infinite, so we can't count it as sig fig.
Correct. Exactly. That's kind of the bottom line. You don't count it. Only the ones that are measured with usually decimals in, but if they're bold-faced though, don't count them. Yeah. Now, what was your question again? The pound? Yeah. Because the unit of an ounce, 16 of them is exactly equal to a pound. If you put a pound on a scale like in our lab in grams, it'll go on. And this one happens to have 5 sig figs, but it probably has in the 90s or 100. I mean, and there's in Paris, we have a perfect kilogram that by world standards, it's exact. And it's under like 5 evacuated domes to keep the air out. It's a big deal. So that's where the SI units come in. Stands for Systemic International, all in Paris. Okay, so good questions on significant figures. Because we're going to do the sig figs throughout the whole semester. So we really need to keep a handle on sig figs. Okay. And then also this guy here. I just finished a lab at Sac City where we were looking at the density of water. And it's 0.999983, just out about 11 sig figs. And then only when you change degrees, it sometimes varies the one way out there. So it's, as far as we're concerned, 1 milliliter, 1 gram. Yeah. It's a good question. His question was, we always round to 2 sig figs, right? All right, it's gonna be 2 decimal places. Yeah. Yes, in our class, yes. Unless you are a Wall Street person, then you get into a whole bunch of decimal places. There's a computer programmer that wrote a program, and it was a financial guy, and he was moving a lot of accounts around, and they always take cents and round them up or down. So what he did is he just took all the rounded parts of the cents and put them in his own account. And because no one ever noticed that the cents, because no one ever saw the 3rd decimal place on their dollars. They always saw 2 decimal places. and it always got rounded. So they didn't realize this. And this person was getting trillions of dollars because the amount of transactions he was going through. And it was all in the Swiss bank account or some offshore deal. And it was a big deal. Very, very cleverly done. And he got caught at it. And I don't know how they caught him. It's kind of interesting how they got caught. But yeah. So the sig figs are interesting. So in here, good question though. Dollars just round to two decimal places. Okay. What do you want to, let's see, what time is it? It's 10 till. I'm going to give you the last semester's take-home question. Now you're going to have a take-home question that's due when you turn your tests in. And it's going to be a long problem. Not going to be a little two-stepper or something like that. It's going to be long, and that hence, and you'll have days to do it. Let me show you what it's going to look like. Got to find out where I saved it. Okay. Let me. Okay, on your take-home test, I'm going to give you this page. And these are some assumptions you are to use when you do the take-home problem. Now, our world is full of data. And there's a problem with that, is that what is superfluous and what is valid. You got to figure out what you need and what you don't need. What you don't need, you just ignore. So your take-home test is going to have this page. And this page has just a bunch of assumptions that you may find totally insignificant regarding the problem I've asked you to calculate. And you have to go through here and say, do I give a flying leap what the formula for coal is? No. Cross it off. World population, number of cars worldwide. How much carbon dioxide was produced in 2011 by forest fires in the United States? Do I need that information? Maybe, maybe not. Okay, so bottom line is I'm going to give you a page of assumptions, something similar to this. And your job is to find out what's given, what you're trying to calculate, and you need conversion factors. And where are you going to get the conversion factors? Two places. One is on this page, and the other place is the internet. This is for your take-home test now. And remember, you're going to have days to do it. So this question is, Okay, so we have California 2020 wildfire carbon dioxide emissions. How many cars burning an annual amount of gasoline would it be equivalent to? So you look on assumptions and look at the metric tons. Now, metric tons is 1,000 kilograms. A metric tons of carbon dioxide given off by forest fires. And it's a whole bunch. And that doesn't count Canadian forest fires. That doesn't count Australian, just United States. Then you need to figure out how much carbon dioxide one car burns in a year. Well, it depends on the car, right? I drive a big truck. She drives, what do you drive? A small sedan? A small sedan. You probably get pretty good gas mileage, hopefully. So can we compare the two? No. So I have to tell you, we're all going to burn 15 gallons per week in a non-leap year. So that means we're going to be burning 52 tankfuls at 15 gallons a tank per year, right? There's a lot of things like that you need to read into this assumption list. And then from there, you can calculate how many grams each car per year is going to make or produce. Then compare that to forest fires. How many cars equivalent is that? And basically, it's just a dimensional analysis problem. It's a real practical one. These are real numbers. Another problem I said, okay, China in 2011 had more coal plants than the rest of the world. So I wanted to know, compare the rest of the world against Chinese coal firing plants, how much carbon dioxide they were producing. So there's always these real world problems that's going to be your take home. But I'm going to give you a page of assumptions that you're going to be using. And a few of them you have to just look up online, but most of them will be on this page. And again, think dimensional analysis. First thing is you cancel out the given and you keep going with conversion factors towards the one you're trying to calculate. Okay, and this will be due on the day of the test. What day is it? The 19th? I have a bunch of classes. Does anyone have the lecture schedule out? It is the 19th. Okay. The 6th. 19th must be my other class. Okay, so that's what I wanted to cover today. Who knows how hot it's going to be on Sunday? 111. Last time I checked in Sacramento, it's going to be 112. And Monday's almost as hot. Like Monday is like a degree less. That is hot. Is this Las Vegas or Sacramento? All right. Anyway, so that's what I'm going to cover today. I wanted to give you lots of examples of dimensional analysis. And on Thursday, I'm going to cover a tiny bit in chapter 1. Things like the difference between a mixture, what's a compound, a few of those, which is basically chapter 1. So in your book, chapter 1 and chapter 2 is for unit 1. Now, if you don't have your book, Dry Lab 1 and Dry Lab 2 are excellent places to go for practice for the tests. Also, if you go to you go to Files, Unit 1, There's a whole bunch of worksheets there as well. And these worksheets I generated, and whenever I generate a worksheet, I always give you the answers as well. And I give you the setup as well, not just the answer. So this is additional. So there's no excuse not having enough practice. You have lots of practice. And basically the test is going to be on sig figs, scientific notation, and dimensional analysis. Most of the points are going to be dimensional analysis. So today's worksheet, Lab 2, is really important, okay? So that's what I wanted to cover today. So I will see you in lab, and we can start lab a little early today. Yeah. 6th. Yeah. I don't know why 19's in my mind. No, okay, good question. The quiz that I have on your lecture is going to be online and it'll be due midnight tomorrow. But it'll be like a 5-question quiz. It's going to be very short. And it'll be multiple choice as well. But in general, I don't give any quizzes in class. I always give them online. Next day at midnight, yeah. It's always, well, 11:59 p.m.